Well, again, folks, in 113, today we're going to be covering sections 1, 3, and both parts of 6.3. Here's a reference to the calendar, just to verify that. Today is Thursday, September 9th, so per the schedule, we'll be covering 1, 3, and 6.3. Okay. The packet that I have for you is kind of hefty. It's a lot of diagrams. This is a copy of an overview of strategies for solving word problems. This is my own personal strategy, how I actually would go about the process of deciphering. Then there's this, which I actually feel is probably even more important. This is a table of words that imply the 4 basic operations: adding, subtracting, multiplying, and dividing. I normally give this to my students as a blank page and fill it in with them, walk them through the process, but for the sake of timeliness, I'm not going to do that. Nonetheless, in Canvas, if you'd like the blank, right, even to keep for your own students and your own purposes, by all means, please take it. All right. This is a list of some basic formulas that would be good to know and a reference to forthcoming things. This is a diagram I have made to describe how this is very basic, one sentence translation here from something verbal to something symbolic, known as the percent equation. Bless you. This is a diagram for ratios, which is another way of really referring to a fraction. This is the inside cover of a marble notebook I swiped, because these are conversion factors. All right, they're not written in the style that would be necessarily convenient, but it's very useful information. And these are 2 sort of models that you could use whether you're trying to convert units or you're setting up a proportion equation. I'll walk you through that. And then there's the actual word problems. These are mine, they're not from the textbook this time. At the very end is something that I think might come up in your MyLab homework called magic squares. So I'm going to give you an example to show you how to do that. All right. So if you're following along, by all means, please print these out, and we'll go through some examples together. Okay. Let me turn on my projector here and make sure that it's in focus. I have to close the window. Yep, definitely out of whack. That's better. Okay, that's not too bad. You know what? This is called the keystone, I believe, because of the shape of it, but whenever I adjust it, to me it always makes things worse. I think that's probably as good as it's gonna get, so I'll leave it like so. Alright, let me show you the 2 things, just so you're clear. Here are the word problems that I normally give to my students when we're in person and we're going through this. There's a lot of empty space on purpose, and for the sake of frugality, I've left out a lot of the diagrams. But the original questions I had part of a PowerPoint presentation, so let me show you that. All right. With a lot of animation, which is why all this stuff is circled. All right. When it comes down to it, when it seems pertinent, I will sort of refer back to this. Like for instance, there's an example of a diagram that looks like a farm. Right, I left that out on the student copy of this, but I'm going to need it in order to actually answer this question. Okay, here again is one of my earlier versions of my table. It's completely blank because what I normally would do, and I encourage you to do this with your own students, all right, give you students the sort of worksheet, right, that is empty, and then fill it in with them, right? The words that imply adding, subtracting, multiplying, or dividing. For a number of reasons, not the least of which, writing something will make you more inclined to remember it. And it's very empowering. If there's one thing that gets sadly glossed over a lot, it's how to translate from English into math, so to speak. Right? Once a kid basically has this tool, or at least is aware that it exists, they're much more comfortable with solving word problems, right, or answering them. Right? So I'm going to switch slides for a moment here. Here's a quick overview. This is, again, what I personally do, all right? You may not end up using all of them, but when you're given a word problem, circle the numbers, right? Because if you have to craft either an expression or an equation from scratch, one is a slightly longer incarnation of a math problem, you'll need to pick out the things that are the actual numbers and include them in your equation or expression. Right? To add a little distinction, I've said this, you'll identify words more likely that suggest an operation. It's usually just adding, subtracting, multiplying, and dividing. Maybe put a box around them. You don't have to put any particular shape, but do something to draw emphasis to them. All right? So circle numbers, box, operations. And then, based upon the description, if there is no picture, all right, they say, that old adage, a picture's worth 1,000 words. Try to draw a simple picture. All right, these are some situations where it would be practical. If you're talking about an area, you're probably talking about a shape, all right, like a rectangle or a circle or something. All right, draw a simple one. It doesn't have to be perfect, and it doesn't have to be beautiful, but it has to sort of summarize what is essential. All right. Same thing for perimeter problems, right? Or if you're talking about points between locations, right? This is what this is implying here. It's a little obscured, but the points would have been A, B, and C. Then there's something that is maybe a little bit more satisfying, but I think people are less likely to do because they're afraid of defacing their textbook. Cross out irrelevant information. Now, I think that earlier on, when you're teaching a kid how to translate word problems, they're probably, there shouldn't be any sort of trickery. It should just be plain, right? They have to get comfortable before you give them problems that are designed, right, to throw you. I don't like problems like that, especially for kids in grammar school. They need structure, and they don't need any surprises. So give them something that is predictable and straightforward, okay? But when the time comes, like usually it's around junior high, middle school or thereafter, right? There's a lot of times a word problem that's written specifically to mislead you, unfortunately, which is to me counterintuitive as a teacher. Anyhow, you can cross out irrelevant information. Especially if you bought the textbook, right? When you're a kid in school, right, that you're borrowing the book, right, and they always would yell at you if you're drawing in it or something. But if you purchased it, don't be afraid to write in the margins when it's important, or highlight something, or cross out something. Right? Here's a very good trick, right? Look for the word "is," right, in whatever sentence or paragraph that you're reading. Because what that implies is that you have an equation, so you're definitely going to have an equal sign. And generally, what occurs before the word "is" verbally is one half of your equation, and what occurs after the word is the other half of the equation. So it's a nice little thing to zero in on, all right? And then there's two things that you can do. You can either borrow a known formula, the kind of thing that would be from a textbook or in the inside cover of a textbook, a lot of times like a physics book or a math book, or you could try to set up a unique equation. Right? Sometimes you have to do that, and sometimes there is the tool already in existence. Right? Now, let me get to this. Identifying operations is very empowering, as I said. So let me show you this. Right? Here is the blank. All right, and again, I would encourage you to, when you're teaching this, give your students the blank copy, and you can ask them what they think. But I would give them a little bit of structure, especially if they're younger. All right, just sort of walk them through the process. Build the frame of reference that they can rely on, right? Because they're just feeling around in the dark. Okay, you got to demystify things. All right, here is what I would have, how I would have arranged it myself since I designed this. Here's that reference I just made before. Is you could translate into the equal sign, the equal symbol. It's not an operation, it's just a mathematical symbol. And these are for specifically English words or phrases that imply mathematical operations, all right? Here's the four basic that we are familiar with. Some things are pretty straightforward, right? The word plus in context implies adding, and then its opposite is minus, right? And then when it comes to multiplication in English, a lot of times we'll say times, right? For division, there doesn't seem to be any sort of equivalent that I can think of. We just simply say divide, right? Then there is, notice for consistency, I made these all the same color in a row. Referring to the operation by the name of the answer. So for example, in the case of addition, you could refer to the name of the answer as sum, right? Or difference for subtraction, product for multiplication, or quotient for division, right? The reason that I put these red parentheses around them is because in order to acquire a difference or a sum or a product, you would need at least two parts, all right? So when you see the word sum in context, assume that it means that you're going to add two things, right? And if you wanted to craft, again, a very bare bones, basic starting sort of expression, right? You could use this one right here, all right? Question mark plus question mark, something plus something, all right? And I would indeed encapsulate it like that, all right? Because when you're talking about a sum, you're talking about two things as a whole, not independently, all right? Then there's these phrases in English, all right? If you notice as we get further down this list, it gets a little less plain and a little bit more vague. Increased by usually just means you're adding, all right? And then it's naturally its opposite is decreased by usually means that you're subtracting, right? These two are kind of a cop-out again, right? Multiplied by is pretty obvious, and divided by is pretty obvious, right? Then there's these, right? More than and less than. They're comparative phrases, right? Beware of these two, all right? I specifically wrote under here, they're counterintuitive, right? These two phrases, although you can get away with any order in the case of adding, because there's a commutative property of addition, you can get away with doing it backwards, right? But to be a good sport, right, a good little math geek, right, you really should do it in the way that it is implied here. A more than B is using B as a reference point, and therefore it would be written first technically, right? So when you're writing it, you're translating it from English to math speak. Put the B in front, whatever this number is, right? So rather than A plus B, put B plus A, right? It is imperative in the case of subtraction that you do that. Again, you can get away with it in not doing it in the case of adding just because there's a commutative property. And the commutative property says that the order in which you do things doesn't matter. But because of the complexity of English language, all right, this is really referring to the second thing, and that reference is what should be written first, all right? Less than is counterintuitively written as B minus A. All right, this is an absolute. You must do that, all right? Even if it is not intuitive, it's counterintuitive. You usually think, well, this shows up first, so why not put A minus B? Don't do it, all right? The thing that is being, the reference point, A is less than something, that something has to be in front, all right, for subtraction. These two things, A of B and A out of B, are very similar, all right? When we get into percent equations, it will be very obvious in this case, right? If it's just the word of, right, it usually just means that you're multiplying two things, right? Now, in the case of a percentage, for example, you may have to convert it to a decimal or a fraction, depending upon whatever you're more comfortable with, or the requirements. But it is intuitively this thing in front times this thing in the back, right? A out of B, right, is basically a fraction, right? I just used the forward slash in this case. But it would be A on top and B underneath it, right? So the first thing out of the second thing, all right? Then there's sort of money speak, if you will, here. Credit and debit, right? Credits are things that are added to your savings account. Debits are things that are subtracted from your savings account or checking, right? These are kind of unique to English, I believe, right? We have a word in English that implies both a number and an operation. So when you say twice, you're saying two specifically times something, or times two, right? There is another one, thrice, technically, right? Which would be times three, right? For division, all right, there are these phrases to look out for. Separately, shared equally, or sometimes the word each. Those usually imply that you have to divide, right? And again, as we go further down this list here, it gets a little less specific, which is why when I filled in this part here, you notice that I made a longer block, right? When you see the word total or spends as part of a word problem, it's a good bet that it's probably going to be at least adding and subtracting, right? It might be more complicated than that depending upon the context of the problem, all right? But you could pretty much count on at least adding or subtracting, perhaps both, all right? It needs more context to specify really, all right? If you're mentioning taxes, all right, taxes are something that are added to a bill, all right? If you're talking about discounts when you're shopping, say for example, that's something that you would subtract from the expenses, all right? So subtract from the bill, all right? To calculate tax, interest, or something called markup, or commission, or discounts requires essentially multiplying by a percentage, which if you feel a little rusty, don't worry about it, all right? Percentages are something that you can convert as an alternative style of a fraction or a decimal, right? When you actually talk about them, people are more comfortable talking about percentages, like they'll say 50% of something, right? But when you're using it, that is to calculate, you would make it a half or you make it 0.5, right? It's the same quantity, it's just a different style of writing, right? Here's another two that are a little more vague, needs more context to specify. Ratios and rates, right? A ratio is basically the idea of a fraction, all right? A fraction is actually a more specific type of ratio if you think about it. I have a diagram I'm going to show you in a minute. A rate is, think of it as being a fraction that has units attached to it, and they have to really be different units. These are signaled by the phrase an or in, or especially per in English, or each. When you see, as I mentioned earlier, things like this on the inside cover of a marble notebook, a big stack of conversion factors. Right? I duplicated this from some book that I had. You see how these are written as something of an equation, really. So like 60 seconds equals 1 minute. Everybody knows that, right? That's interesting that it went pink. 60 seconds equals 1 minute. That would technically be written in the style of an equation, right? But when you're using it, because of the equal sign, but when you're using it, all right, you would write it in the style of a fraction. So whatever is sitting on this side of the equals and whatever is sitting on that side of the equals, you would stack like this, more or less. A ratio would be technically more correct to say. All right. When you are using the ratio or the rate, it's a conversion factor oftentimes, you're frequently multiplying it, right? But unto itself, right, by itself, you just consider it by itself, or autonomous from everything else, it actually represents division, because what is a fraction but basically something divided by something else, really? This line is another way of saying division, right? That's a lot to swallow, all right, but don't be intimidated, right? This is, again, something that you can have, all right, to refer back to, right, and maybe refine more than I have, all right? Let me show you this other diagram, since I've just broached the subject of ratios, all right? A ratio, again, is the idea that we have of a top number sitting on a bottom number, right, which is why I put this cloud here, right? A fraction would technically be a more specific type of ratio, right? This may be a little hard to see from far away. But fractions are just purely numbers, right? They're unitless. There is no decimal point in the top figure, and there is no decimal point in the bottom figure. And formally, this is referred to as numerator and denominator, of course, right? If you are a little less, like, that's more strict to call something a fraction. If you're more general, less strict, right, we're talking about a ratio. And it could be anything sitting on top of anything else. So some kind of a decimal number, like 2.5, sitting on top of 3, right? You wouldn't call something like this a fraction, even though it basically, again, is the idea of a top number sitting on a bottom number, because it's technically not. It has a decimal there. This thing by itself would be considered a fraction, right? Anyhow, there's the sort of verbal way of referring to it, which is to use a colon, right? In the United States, when we talk about division, right, we use the colon with the line through it. But elsewhere in the world, right, they just simply use the colon, right, to talk about dividing, right? Or it could be written somewhat verbally here. You could say, again, the word to, or the phrase out of, right? So if you see it sort of more concisely writ, it would be A colon B, right? Or if it's a little bit more verbose, it would be A to B, right? First thing to second thing. Or A out of B. Anyhow, if there are any units involved in something that is purely a ratio and not a rate, they are the same type of unit at worst, and they would cancel in theory. Right? And when you get into a true rate, right, it again is still any number on top of any number, top and bottom, right? But it has two different units involved, right? And the units must measure different physical quantities. So there'll be, like for example, famously on street signs, we have this abbreviation, right, MPH, which stands for miles per hour, right? This is how it looks on street signs in the United States, MPH. Miles per hour is what it actually stands for in English. And if you wrote it in math speak, right, it would be miles above the line and hours below the line, like that. More or less like a ratio, glorified fraction. Okay? The units measure different physical concepts, right? And a lot of times these are examples of conversion factors, right? They translate one thing into another purposely, right? One unit into a different unit, right? If you have something that is referred to as a unit rate, the actual division has already occurred. So like if you saw something like this, 2.5 over 3, that would be, like, let's just say miles in 3 hours. It's a rate in this form, right? If you actually did the division of 2.5 and then divided by 3, I'm going to cheat right now and use my calculator. 2.5 divided by 3, sorry for the glare, is 0.83 repeating. Having done that division, having arrived at that quotient of approximately 8.3, you could rewrite this in the unit rate style, which would be 0.83 miles over 1 hour, right? What you do to make a unit rate is that you write the quotient over 1. Okay? Then in finance, there's something called, well, ordinary life. A unit price or a unit cost or something about that is referring to money, all right? As a technicality, all right, because you're talking about money, you're referring to something, if you're talking about something in reference to money, regardless of how it is arranged grammatically, first or second in a sentence, the top number represents money and therefore must be written on top. So, no matter what, you're going to have money above some unit. Right? So if you happen to be living in the United States and use dollars, it would be dollars on top, even if it was written at the back of a sentence. Right? It's a little counterintuitive in that regard. Here's yen, here's euros. I had the symbol for rupees, but it got erased somehow. All right, anyhow, the top number represents money in the front, not behind. Oh, that's another thing. It's not really a pet peeve, but money is not a unit in the classic sense. Right? A unit is usually comes from something that has been measured. Money is not measured with like a meter or something like that. It's counted. So to add some distinction, perhaps, right? When you're referring to an amount of money, like say $5, right? You must put the dollar sign in the front, right? I've seen a lot of people put it in the back, but that is an error, right? That is implying that this was measured, and you don't measure money. Alright, so $5 per, let's just say 1 pound. Alright, LB, which is Latin. Dollar sign in front, pounds, if it's something obviously measured is weighed as well. Weight is measured, right? You put the pound symbol in the back of the number, not in the front. Okay? Alright. Here again, some other references for rates. A per B, a for B, a in B, a and B. Okay. Now, let's talk about this. All right. Here are some basic formulas again that are good to know. I'll erase this. The area, the perimeter formula, there are specific formulas for specific shapes, right? But in general, the perimeter is a measure of the distance around something. And therefore, if you have actual side dimensions, you could just add all sides, sum of all sides, whatever shape it is, all right? For area, this is specifically the area of a rectangle. You can get away with using this for a square, but a good thing to know is the area of a rectangle, technically a square, also would be length, or coincidentally, if you have a square, it is also a rectangle, because it has right angles. It's just length times width, so something times something else, all right? There's the Pythagorean theorem. This is specifically for right triangles only. So don't apply it to anything unless you're talking about a right triangle. And a right triangle is something that has that box in the corner that represents a 90-degree angle. So if you see that, or it's actually mentioned as a right triangle, all right, you could in theory use the Pythagorean theorem. It's really the side squared plus the side squared plus equals the hypotenuse squared. A lot of times it's written as abbreviations, so I might call this a squared plus b squared, and this is c squared. All right. The things that are the sides are the things that are around that corner. All right. So they're interchangeable, right? Because they're both the same type of thing. They're both the side, or sometimes they're called a leg. So this would be, I prefer to call this B as in bottom and A as in altitude. All right. The one thing that is non-negotiable, the thing across from the box, is the hypotenuse. All right. So that's always C. You must use C for that one. These two you could switch, wouldn't matter. Okay. Then there are these two, which are basically very similar. All right. The distance formula is equal to speed times an amount of time. This is an average distance. All right. The average distance based upon a number of gallons. All right, your miles per gallon gas consumption rating in the United States, we use gallons for fuel. all right, times the number of gallons would also give you an amount of miles, right? You can rearrange algebraically any one of these three parts, and similarly rearrange any one of these three parts, they're a number, and solve for the thing that is missing. Just the golden rule of algebra is that you have to have the majority of information. So if you have three parts, you need 2 out of 3, right? If you have 4 parts, you need 3 out of 4, right? Now here's another thing which may seem a little silly, but I find it useful anyway, especially for a total, things that involve money, right? Or if you have a word problem and it's very vague, all right? Start with this scaffolding, right? This skeleton that you could slowly but surely flesh out. Sum total quoted to you minus whatever amount is known would naturally leave you with what is unknown, right? Again, that may seem kind of silly, but it's nice to have this as a starting point, a launching pad, if you will. Okay, so these 1, 2, 3, 4, 5, 6 things are basically some good things to start with in terms of equations. Then there are these things which are a little bit more specific conditions, proportions and percent equations. Right? Let me show you this first because it's a good point to segue into translating very simple word problems. So we'll look at that. All right. Here's this diagram. There are basically 3% equations that kind of grouped together like this. It depends on which portion of the problem you are actually looking for. All right. If you're looking for a piece of something as opposed to the whole or original amount of something, if you're looking for a piece or some final amount, then you're looking for a part. All right? This is a portion equation, if you will. If you're looking for the original amount of something, or more or less the whole, that's referred to as the base. All right? So this would be the base equation we'll talk about here. All right? And this is the one that you're literally looking for the percent, which is probably the most obvious, but is the one that involves the most steps. Right? It's a ratio of 2 things times 100. All right. If it says what percent, you pretty much know that you're going to use this version of the percent equations. Now, what are some operations involved here? The part equation, if you know that you have that, is purely arithmetic, meaning what you see is what you get. If you arrived at the conclusion that you're going to multiply, then there's no trickery, you're just going to multiply. In these 2 instances, these are technically going to involve algebra because you're going to end up performing an opposite operation, right? So what that means realistically is that you're going to probably end up dividing ultimately, right? This one, the percent equation, again, the most obvious to recognize but the most involved, you're going to divide. It's going to be more or less an algebra problem. But you're also going to multiply by 100 in order to formally write something in the style of a percentage using that symbol, right? Here are some signal phrases in English. Make this a little bit bigger. Right. When you see in context the phrase, what is, blah, 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 right? It usually is something like, what is 50% of something? Right? That's a cue that you're looking for the part. All right? If you see is what, all right, which is the same thing, just sort of phrased backwards, again, you're probably looking at it doing or using a part equation. All right? To add some distinction here, if you see the phrase of what in English, there'd be something written before it and something written after it. All right? Of what is a cue that you're looking for the base in the equation, right? Sort of the original amount of something or the whole, if you will. Right? And again, very plainly, if you see the phrase, what percent, they may spell it out, P-E-R-C-E-N-T, all right, or they'll use this symbol, all right? what percent is, you're definitely looking for the actual percent. All right. Now again, I like teaching this, and I would encourage you to use this as an instructor yourself. All right, I created one problem that I'm going to be looking for the individual pieces, part, base, and percent. All right, we'll decide that based upon what's missing. All right, referring back to this diagram now. All right, the reference built of words that refer to one of these operations. Look what you have here. If you had this very simple one sentence long word problem, all right, it's a good place to start again. And you see 50% of 20 is what? You might intuitively know what the answer is, because you might know that 50% is just half of something, right? And if you do know that intuitively, good, all right? Intuition is never something I want to talk a student out of, but we're trying to arrive at a strategy. And so humor me for a moment. The word of means multiplication, right? The word is the symbol that is equals. The nice thing about this is that it's pretty straightforward, all right? Whatever's sitting around the word of, on its left and on its right, would be just written into the equation in the same way. So whether you put a half or you put 0.50, it's going to be on the left side of the word of the multiplication symbol because of the word of here, and 20 would be just on the opposite side, right? And as you can see, it's a number times a number, so it's purely arithmetic, no trickery, right? Again, that's the decimal version of this, right? If you feel more comfortable, you could just as well put a half, because 50% is a half, times 20, and then just disguise it to look like that as well. A fraction, but we want to do it. I think because people are more inclined to use the calculator, then we're probably more likely to use a decimal point. But if you understand the concept of a fraction of a half being really the equivalent of 0.5 or 50%, you could sort of circumvent needing an calculator, because it's just half of 20, which is intuitively what? 10. Right? So 0.5 times 20 would just produce a 10, and that's your answer. That's a part of the original whole amount of 20. Right? Now again, because I'm not too creative and I'm trying to make things predictable, I rewrote the same problem but looking for a different piece here. All right? Different part. Chunk, if you will. All right? Let's do the same thing. All right? If you have 50% of, start with writing multiplication x. And if you see the symbol is, the word is, put the equal sign, all right? Drop what is next to it here, all right? So if you see, again, 50%, you can make that a decimal to use it, so it'll be 0.50. And now there's a 10 over here, so you're gonna put a 10 on the opposite side of equals. When you see what is in the middle, that means that the base is missing. So I'm just gonna put a B here to represent base, all right? Now I'm going to assume, perhaps wrongly, that you've probably seen algebra before, even if it was not your favorite subject, and I won't want to talk you out of it. All right, this is what do you call it? A one-step algebraic equation, right? In a nutshell, all right. To solve algebraically, what do you end up doing? Do opposite operations, essentially. So when you're translating, you translate it of into times, right? But what do you end up doing instead to justify moving something over the equal sign from here to here, right? To isolate B and therefore to solve for B. You perform the opposite operation. The opposite of multiplying is what, right? The nice way of writing that would be like so. Right, I'm going to write this over here because I need the space. Right, 0.50, I'll add some distinction by making this red, and I'll just sort of press them together. You can put the dot if you like. All right, and this equals 10. In algebra, they have a tendency not to use the colon with the line so much. They use just this bar when we say, okay, if I'm going to perform the opposite operation, the opposite of multiplying is dividing. So I'm going to divide by 0.50 here. And then to get away with it, legally speaking, I'm obligated. If I've done division here, to balance it, I have to do the same thing here. All right? By design, there's going to be a cancellation effect. All right? Something divided by itself strategically cancels, leaves me with the thing that I want, and then I have the arithmetic portion of the shell here, which I could just do myself, or you could use a calculator. 10 divided by 0.5 is 20. Right? That's the base. Right? Of what is of 20? And again, I'm not too creative, I just did this here. Alright, I rewrote the same problem but with a missing chunk missing. Alright? A different chunk missing. What percent? Alright, so you see in this case, what percent of 20 is 100? You probably know, well, it's got to be 50. I did it twice already, or talked about it in reference. But let's set it up, right? This is a good habit. What percent? Let's use a letter, we'll just call it P, to represent the percent. Right? Of is still going to start out as times. Right? 20 is still sitting on the opposite side of it. The equal sign is still represented by is, and there's a 10 sitting over here. Right? Now, because we have, as we did just a moment ago, a letter times a number, this is a number times a letter, as opposed to just a number times a number. It's not pure arithmetic, it is once again an algebra problem. So that means in order to solve the equation, we have to perform the opposite operation to justify moving stuff. Right? Algebra is a technique, right, we employ. So, I'll do the work up here. You could leave it exactly as you see it. That is to have, maybe write in black, because it'll be easy to see. P times 20 equals 10. Or you could, write it in the more concise way, which according to good etiquette would be to put the 20 in the front. Doesn't really matter. And then move stuff around, namely move the 20, the coefficient is the fancy way of saying number sitting in front of a letter, to the opposite side to solve, that is, get this alone. Right? So the opposite of multiplying by 20 is again to divide by 20. And if you've done it here, your hands are tied. You're obligated to balance by doing the same thing here. So, by design, every single time, something divided by itself is what? It's 1. The only exception is you can't divide by 0, technically, right? That leaves you with what you're looking for, which is P. And then you have 10 over 20, which, pull some tricks, pair of zeros would cross out. That's a half. All right? And we're going to have to write the fraction in the style of a percentage. That would be the top thing divided by the bottom thing, and then times 100 is basically moving the decimal point. So what I like to do a lot of times if I have a fraction is just draw the division box immediately next to the bottom, the denominator. Put the top in here and throw in some zeros. All right, and then you can do long division, all right, or short. 2 doesn't go into 1. Too small, but 2 goes into 10 exactly 5 times, which would be 10, and it terminates and you don't need these. So you have now the decimal equivalent. If you then go the whole 9 yards and multiply by 100, the effect is that the decimal point would move 2 spaces to the right when you multiply. So scoot over 2 spaces, fill in the wave here. You would end up with 50% one way or another, right? All right. Again, I like to introduce these because they're the beginnings of translating in a fairly straightforward fashion from what is English to what is purely math, right? And English could be very confusing, certainly, all right? So beautiful language, but it has some issues, right? When you're teaching math, right? So of is times, is equals. Those are very powerful, very simple tools, right, to bear in mind. Okay? let's see what to do next. All right, let me show you something else, and then I promise you we will finally get back into word problems. All right, this I'm going to take from my actual presentation that I had earlier. This is not part of the slides that it will be available. Well, I think it is actually, but you don't have to print this. This is a lot of paper. When you get into algebra further in the semester, right? Again, that little trick, sort of zeroing in on the word is invaluable. All right, and here's why. Right? You would have here's the description of a sentence rather than an actual sentence. I'm going to zoom in on this just a wee bit. Okay. It's supposed to look like a chalkboard, right? Right. You have the words before, and then there's suddenly the word is, and then you have the words after in English, right? If you recognize that is represents this symbol, right, then that means that the words before would be basically 1/2 of the equation, right? And that the words after, again, would be the second half of the equation. Could be shorter on this side or equally long or even more complicated, but that's how you could, this is the skeleton that you could rely on, basically. The whole thing, the whole kit and caboodle is referred to as an equation. If you do not have this symbol involved, you're not dealing with an equation, really, right? The parts from which an equation is made, the things that are on each side of the equal sign, they're referred to essentially as expressions, right? Anything could be an expression. The number 1 sitting by its lonesome on one side, that's an expression, okay? It's usually more complicated than that, and in algebra they throw letters in too, but just understand an expression is more or less the building block, and the equation is the entire house, okay? Here's another thing that's interesting. You can cancel like factors above and below sort of the fraction bar, okay? Now, when you're dealing with fractions, like let's just say that you had 1/2 times 2/3, all right? You could do it brute force. There is no sin in that. It's just less efficient, which is to multiply the top thing times the top thing and get a 2. And the bottom thing times the bottom thing and get a 6. And then as an afterthought, divide by the GCF, the greatest common factor, the thing that makes both a 2 and a 6, which would technically be the number 2, and simplify as an afterthought, as a last step, which would produce 1/3, right? That's your answer. Or you could do the thing that is, when you're more comfortable, more strategic, which is to take advantage of this, that if you have like factors, one thing above, one thing below, right, you could simply cancel them or simplify them even if they're not just identical, right? Like let's just say that that was a 4 here and this was a 2 here. They're both divisible by 2, so you can simplify, right, before you multiply, right? That would leave you with just 1/3, and you get to the answer that much faster, right? The nice thing about this is that that is also true when you're not dealing with actual numbers. So if you had a letter like this, technically, x over x, right? I don't even know what it is. This looks like blood. Sorry. All right. If you had something over itself, all right, assuming that x is not equal to 0 itself, this would reduce to the amount of 1, even though you don't know what it is. The only assumption that you would have to make is that it can't be 0 because you can't divide by 0 legally. All right? Something divided by itself is 1, right? That's true not just for numbers, but for letters, and for words, and for abbreviations for words. Like, for example, FT is the abbreviation for feet, right? So if you had, essentially, as part of some problem, something feet over something feet, you could cancel out the units. Right? That, again, is just a very simple thing, right? But most people just take it for don't even take it for granted, right? They should. All right, they should be aware, is what I'm saying. All right, it's very empowering, all right, to a student to know that. All right, let's do some examples now. Finally, sorry for the delay. All right, and I'll try to implement these strategies that I'm referring to. All right. Here's the first example of a word problem. All right. If I take my own advice, which is to circle the numbers and put a box around the words that imply an operation, I'll do that now. Okay. All right. Sometimes the numbers are obvious, so this 3 is an Hindu-Arabic numeral 3, so that's cool. 5 is sort of disguised, so just put that in its Hindu-Arabic numeral style. And there's another thing that's spelled out in English, 7. So probably, unless somebody is trying intentionally to confuse me, I'm going to incorporate a 5, a 3, and a 7 when I write my expression or equation. Right? Another little thing to pluck out, there's is here. So I know that I have an equation. Right? On a nice empty space, I might start with that then. Equals. Right? All of the gobbledygook that shows up before the word is going to be half of this equation. Right? I could start with that immediately if I wanted to. Right? 5 less than 3 times a number, right, is the same as equals on the number increased by 7. Let's start with the left half here. Less than is one of those counterintuitive operation phrases, right? Less than refers to subtraction, but just remember, it's counterintuitive, meaning it's the opposite of what you would think, essentially. Even though 5 shows up in the front, and it would be totally understandable to go, oh yeah, sure, 5 minus 3. Don't do that, right? Less than, you see this than comparative phrase in here? Put the 5 in the back, right? Immediately. The other thing is a little bit more straightforward, all right? 3 times is 3 multiplying something. When you're confronted or given something like a number, use an abbreviation that would be intuitive. You could use an X or something, but to me, I always go with the first initial. So if it's a number, call that N, right? 3 times N minus 5 is essentially this half of your equation, right? You could always clean it up, refine it as an afterthought, but that's good to start with, right? Now there's the right side here. Is the same as, that's redundant, as the number and again, increased by 7. Increased by is another operational phrase, so it's plus 7. That's the other half of this equation. All right. Now, if I were conforming to good etiquette, pinky in the air, sipping tea, in algebra we stop using the multiplication x because we don't want to confuse it with the letter. So they might use a dot or simply throw these things together, in which case you would have this expression, 3n minus 5 equals, that's more concisely written, right? And then on the opposite side, n plus 7. Okay? Now, we have an algebraic equation, right? And we could start employing algebra at this point. Perhaps you're a little rusty. What I'm going to do on probably tomorrow is Friday is I'm going to shoot a video for 090, which is algebra. All right, but to get through this, what I have to do essentially is move stuff around. And you see that I have letters on opposite sides. I need to bring them exclusively to one side. So what I'm going to do is I'm going to move the n from here over to here. All right. When you go over equals, use opposite operations. So if this is really positive 1 with an n attached to it, if I want to justify moving this chunk from here to the opposite side, I have to perform the opposite operation. This red is getting a little dead. So opposite of adding is subtracting. All right, and then I'm going to park it under its friend here that it most closely resembles. And then just for the sake of space, I'm going to move the 5 simultaneously. All right, this one's maybe a little bit easier to figure. Subtracting 5. The opposite of subtracting 5 is to add 5. So I will add 5 here and add 5 here. Right. There is, by design, right, a cancellation effect. Something minus itself goes away. You could put a 0 if you like, but it isn't necessary. Then over here, these things, all right? Granted, I don't know what n is yet, but I know that it's something minus itself. So by sheer logic alone, something minus itself has to cancel as well. All right? And that leaves me with the work here and the work here. Right? What is 3 minus 1? 2n, right? There's still this equals here. And what's 7 plus 5? 12. So what this ends up being in reality is 2n is equal to 12. Right? Still have to perform algebra because I haven't quite isolated the letter yet. Right? But it's understood that a number pressed against the letter is being multiplied, at least to start with. And again, if I want to justify moving 2 from here to here, when you go over equal, you use the opposite operation. The opposite of multiplying is dividing by 2 and balanced by doing it to both sides. Okay. So something divided by itself cancels, it's 1 technically. N is what we're looking for. That's left over, very good. And then the answer is whatever 12 divided by 2 is, which should be 6. If you wanted to check, you could throw it into here. 3 times 6 is 18. And 18 minus 5 would be 13. All right, 6 plus 7 would also be 13. It balances, it's correct. Okay? All right, moving up. All right, here's an example of where you have information that is irrelevant sort of thrown at you, right? But don't be deterred. Right? Remember what I said before, right? You could start by doing the easiest thing, which is to pluck out the numbers involved by simply circling them. So whether you end up using them or not depends upon the context, more information, right? So I'm going to just innocently do that now. A 5-speed Jeep Cherokee gets 23 miles per gallon, right? Here's a 5, and here's a 23, all right? On the highway, all right? How many gallons of gas would be needed for a 667-mile drive from El Paso to Dallas, Texas? All right, now, this is an example of where you could cross out irrelevant information. All right, this number 5 that is here. 5 speed is a description of the transmission of a Jeep Cherokee, right? That is really going to be deleted. Let's say that you didn't know that immediately. By reading the rest of the problem, and it's asking you how many gallons of gas would be needed for a 667-mile drive, right? You have in your arsenal, in your toolbox, a list of formulas, all right, that involves this, all right? A distance is quoted here, gas consumption rating, miles per gallon, and a number of gallons, all right? So we could start by borrowing that. We may have to refine it, but look what you end up with here. You have distance is equal to the rate, which is known as miles per gallon. The reason I know it's a rate is because there are 2 different units involved here, and the word per, right? And then times a number of gallons, because this is the U.S. apparently, all right? All right, So I have a skeleton that's already available to flesh out, right? There's a distance quoted to me here, right? So in place of this distance, I can put 667 miles, right? You can put the unit or you could forego it for the time being. I'm going to keep this black. My red is getting dead, so I'm going to give it a rest and steal another one here. The gas consumption rating, miles per gallon, is 23 mpg. So I'm going to put in here 23 miles per is this line, 1 gallon. I'm going to be perfectly twitty. All right. And then I have to actually figure out the question of gallons, right? That's the one thing that isn't actually included as a number. That's what we're looking for, how many gallons. So you could leave this as G if you want to, right? All right, now, to get back to my original point, since this is just 3 parts, and I have the majority of parts, 2 out of the 3, I don't need anything else, and that would actually answer the question. So this information, a 5-speed Jeep Cherokee, although it's interesting to say about its transmission, it's irrelevant. You could cross it out. You might have intuitively done that to begin with, all right? Now, to spare yourself a little bit of trouble, when you're actually trying to arrange this to solve for G, gallons, what you might do is use abbreviations without the substituted numbers. So I'm going to put D for distance, M for miles per gallon, and G for gallons. All right. I'm going to take advantage of algebra, the process of rearranging stuff via opposite operations, before I do my substitution. I only put the substitution in there to illustrate this point. If I want to solve for G, then I more or less have to freeze that in place and move this to the opposite side. If these two things are being multiplied, then in order to legally justify moving them, I would have to perform the opposite operation, which is to divide by M here, the concept of miles per gallon. And whatever I've done to this side, my hands are tied and I'm obligated to do to the opposite side. That means that realistically, this would cancel. This is the incarnation of the problem that I would be working with. The rearranged version of this, which would be gallons is equal to a distance over an mpg. Right? And in this case, because I've done the algebra to rearrange this to begin with, I'm left with pure arithmetic, just numbers that I could punch into a calculator if I needed to. The distance was 667. Right. And the mpg was 23. Right. And what you should end up getting is what? 667 divided by 23. You should get 29 gallons is what would be consumed from such a trip. Okay, so this would be equal to 29 gallons. If you're concerned about the units, and in the case of a science class like physics, you would have to take that into consideration. The minutia of what would be involved here is the following. Miles would be above the line. And mpg being what it is, a rate, it would be miles per gallon here, right? What that really ends up being is a fraction divided by a fraction, which would be miles divided by miles per gallon. So you can make it miles over 1. And if you, maybe perhaps you're a little rusty, but if you remember, when you divide fractions or even things that simulate them, right, you end up multiplying instead by the reciprocal. So you'd have miles down here and miles here. And just as I mentioned earlier, all right, numbers that are like factors above and below the line cancel. Well, that is also true for words and for the abbreviations of words. The bottom line is that you'd be left with gallons as a unit. If you don't want to worry about it, that's fine, right? Because we have this equation which is tried and true and trusted, all right? And you really don't have to worry. It produces gallons as an answer, all right? But that's the fine detail of what would actually happen in terms of the units. All right, in a physics class, you have to be a little bit more on top of that. Okay. Let me continue. This example, there isn't the actual building involved here, so I'm going to just draw it really quickly. All right. This is an example of a word problem that requires a picture given to you and a certain level of comfort with algebra. All right, let me draw the picture that I neglected to print here. Arrange your most fence in a corral as shown. This is basically the shape of the corral. And there's a barn here. And the dimensions of this corral are outlined by this sort of L shape. Right, the figures you would have involved here are the following. Right, it's 300 feet this way and 475 this way. 275, 200, and 200. Right, and since this is attached to the barn, there's no need to put up a fence there. No fencing is required across the barn entrance, which would be presumably there. It's not very pretty, huh? You're looking at it from the top down. If the fencing cost $4 per foot, what is the total cost of the fencing? All right, a couple of things are at play here. We have a diagram that's given to us that involves fencing, all right? When you're talking about a fence, right, you're probably discussing a perimeter. Right? If, just out of curiosity, if you're talking about carpet or something like that, or painting something, that's probably referring to an area. So, of these two things, perimeter is what we have to do, which is just adding a bunch of sides. All right? Add all sides. That concept would be good to know, all right? Then there's this, if the fencing costs $4 per foot, we have a rate going on in here. It's $4 per foot is a different unit, so to speak. So if you have $4 per foot, you would write it like this in the style of a fraction. The 4, because it's money, would be on top no matter what, all right? And 1 foot, which follows the word per, would be obligated to write in the bottom. I'm using the abbreviation FT. What is the total cost of fencing? That phrase, remember, total cost, right, is vague, or more vague than other things, because it might be adding, it might be subtracting, it might involve something more complicated. All right. Let's figure out a couple of things. All right. If we're talking about a total cost, it's not really helping us too much, but we could logically talk ourselves through the process. The total cost would be, all right, total perimeter in feet times the cost per foot. right? So if you had 1 foot, you're going to spend exactly $4 because of this relationship here. But you would expect naturally that it has to be something, magnitudes larger than that, right? All right, so if you had 2 feet, it would be 2 times as much, right? They didn't say the word times, right? But when you're talking about a rate, as you see here, right, by itself it represents a fraction, which is a glorified division problem, right? But when you use it, as I mentioned earlier, it usually is multiplying, right? So look here again, just for reference, not double talking here. All right, we have a rate involved here, right? When it's applied, it's often multiplied, okay? A ratio or rate. So it's very subtle in this case. All right, now if I could clean this up a little bit, total cost would be, let's just call this equals. And I'll just go down to total here. Total perimeter would be what? It would be all of this stuff added together, right? So I would have to do that first, calculate that first. A sum, essentially, of 475 plus 300 plus 275 plus 200 plus 200 feet. And then after I calculate that, multiply by this conversion factor, essentially, which is $4 per 1 foot. What's going to end up happening is that the feet unit are going to cancel. All right, and that leaves us with the total cost, which is what the question is actually looking for. Okay? So what you should get is 1,450. A little short on space, so I'm going to put it over here. 1,450 feet. All right, again, times $4 per 1 foot. All right. And again, although it's not written exactly in a fraction, you could disguise anything as a fraction by sticking a 1 under it, right? Similar looking features above and below the line will cancel. And that leaves you with 1,450 times 4, which should leave you with 5,800, I believe. Let me just check here. 475 plus 300 plus 275, 200 plus 200. Here we have the sum of the dimensions of the fencing, 1450, times 4. It's indeed $5,800. Okay. So this is $5,800. Okay. All right. Let's talk about this. I like this problem because this is a good segue into proportions. Okay. Let me maybe do something first and then come back to this. All right. Let's talk about proportions as a concept first. You know what, let me do one other thing too. There is one word problem that I left out, but I just want to point to it. It's in my original PowerPoint presentation. The instance of when you have to sort of draw a picture, all right? This is the original problem. It's not part of your packet. It says Mary travels from Columbus to Indianapolis and then on to Springfield, 3 places, all right? No illustration. If the distance between Columbus and Indianapolis is 168 miles and the total distance is 351, what is the distance between Indianapolis and Springfield, which is a different segment? This is 2 things going on here. A situation where you have a description of a point A, a point B, and a point C. So if there is no illustration, you could draw a very simple picture. Nobody says north or west or anything. So just draw a straight line, but make little dots like this. All right. Then based upon the description, fill in the void. If they say from Columbus to Indianapolis is 168, then you would just sort of label that segment 168, right? If they then tell you that the whole total from here to here is 351, then what that implies is that the missing chunk here can be figured out. You'd have essentially the majority of information, everything that you need to know. The second thing that is useful here would be that sort of silly sounding equation, which is that the total minus the known would logically give you the unknown. Right? You have the sort of mental exercise of drawing a picture because they didn't give you one, right? And then you borrow this sort of scaffold here, this skeleton, right? Total is 351. The known chunk is, just from here to here, is 168. And that's just pure arithmetic. So what you would end up with is whatever 351 minus 168 is. All right, 183. Okay. Now let me move on. All right. Take a look at this unit conversion. All right. The last problem that I had done that was part of your packet was a conversion factor kind of problem. All right. This is a little hobbled together here, but there's similar looking concepts. That's why I put them on the same page. All right. And I'll sort of explain it now. All right. There is this sort of scaffold machine, whatever you want to call it, that you could use. All right. If you know that you have a unit conversion factor, like that last problem was $4 per foot, all right, then you could write it in the style of a fraction intuitively, because per is this line, right? The thing that was given to us was that, well, we calculated was 1,450 feet, right? If we strategically rig this sentence, a fragment of the sentence, to fit in this chunk of the machine, if you will, we would do exactly what we had done, which is that the $4 would go here, per is this line, and the 1 foot abbreviation would go there. Right? And again, it's like I keep mentioning, things that are diagonal more or less can cancel, and that leaves you with feet, which is why you end up with $5,800, right, in that last problem. Let's call this a unit conversion machine for now. All right? It allows you to convert between different units. The different unit technically would be $1 and a foot. All right? Just that this unit is not measured, so we put it in the front counter. All right. This makes use of something that you might call a cross simplification technique, which is basically dividing. It's dividing this by this without really consciously being aware of it. Something divided by itself cancels, right? I.e. that like symbols will cancel diagonally. I tried to illustrate that here with inches and centimeters, right? Again, if these things are more or less, one is above the line and one is below the line, they cancel, right? The minutia is that they're dividing, but you're not really thinking about it, and you don't have to worry, right? Then there's this other little thing here, which is a proportion type of problem. So that's why I put this sort of dashed line here on the page. Because they're similar looking, and they have similar sort of techniques, but they're not to be confused really. Right? This is what you might call a proportions machine, shall we say. And it's the kind of thing in a practical world where you would allow you to sort of enlarge or shrink a photograph, upgrade or downgrade, you might say, the dimensions of a picture without actually distorting it. Now, when you're a kid and you go through school and you have your school photograph, right? A lot of times the packet that they sell you is 3x5, a wallet, a full 8x10 photograph, what have you. But they don't just stretch your head to make the picture, larger or smaller, right? It's not distorted when they enlarge it. How do they make sure that it's correct? They use proportions really in order to do that. The measurements have to be consistent. This is the machine, all right? It's a little different, and you got to make this distinction. This looks like a fraction times a fraction, right? And it is. Right? It's essentially a fraction times a fraction if you have a conversion factor, the unit conversion machine. All right? It's a fraction times a fraction, essentially. This is not a fraction times a fraction. This is a fraction set equal to a fraction. Okay? This is a little bit more straightforward. It usually is the top times the top and the bottom times the bottom. And that's what you're left with. When you have a proportion machine, shall we say, we don't do it that way. We don't do this top times this top, this bottom times this bottom. What we employ is a cross multiplication technique. Right? It is actually multiplying rather than when I did simplification before. Right? It's essentially multiplying diagonally, which is why I put this little diagram here with this little sort of nucleus symbol. All right? The model often is abbreviated with A and B and C and D. Right? What that means, if you multiply diagonally like this, is that on one side of the equals, you'll be left with B and C multiplied. And then on the opposite side of the equals, you'll have A and D multiplied. All right? All right? So, how to fill this in, all right? The trick is you need 3 out of 4 parts, right? And you must be consistent, right? What do I mean by that? I mean, if you're talking about shapes, all right, take the dimensions from the first shape and put them in the first fraction. Then when you're filling in the one piece of information that you have for the second shape, make sure that it corresponds to whatever the part is, right? So you want like things to be consistently written as the top figure and or consistently written as the bottom figure, right? There's more than one way to arrange these things, but be consistent. You can get away with a lot, but you got to be consistent. Okay? Now this problem that I mentioned earlier, I'll go back to now, from here, involves moose population, right? I like this because it's a good example of where you might employ a proportion equation. It's all off the page here. A biologist wants to estimate the number of moose in a wildlife preserve, right? She captures and sedates 250 moose, tags them each, which is probably putting something in their ear, and then releases them back into the wild. After several months, the biologist recaptures 120 moose at random and notes that of those, 4 have tags, right? Assuming that none of the moose have lost their tags, approximately how many moose on the preserve are in the preserve total? This is an indirect way of counting a population without having to somehow find them all and pointing at them and going, there's 1, 2, 3, right? That would be rather tedious, and you'd probably make a mistake. When you have something like this sort of indirect measure, you could use a proportion equation, which essentially is something over something is equal to something over something. A fraction set equal to a fraction. That's the skeleton that you're going to use, that you're going to flesh out. And cross multiplication is the technique that you will use to solve. this equation, all right? Now just be consistent, all right? Decide what the top of the fraction represents and what the bottom of the fraction represents off the bat. All right? These are different sides. Let's say that we have tagged animals as the top and a total as the bottom, all right? So in this first one, this is so many tagged, and this is so many total, and this is so many tagged, and this is so many total, all right? Be consistent like that, all right? She captures 250 without saying the word total. So I'm going to put 250, well, 250 is a portion of the whole, so I really should put 250 with tags up here, right? All right, and the total would be the actual X total population, right? That is mysterious, right? Later on, all right, several months later, the biologist captures 120 total, all right? That would be 120 of those that she has in her possession. And of them, how many have actual tags? Only 4, all right? So this is one way of arranging it, right? There's 250 initially with tags out of some larger quantity of actual total population. And this is represented later as 4 out of 120, all right? Because that is a smaller chunk representative of the whole, all right? If I were just gonna sort of trim it down to the essential information, all right, it would look something like this. 250 over, I just like the letter X, so I'm going to use X for this missing chunk, the total, to answer the question. And over here I'm going to put 4 over 120. All right. Now if you'd like, you can simplify this fraction. All right. 4 and 120 would reduce to 1 over 30, right? We'll leave it alone. All right. It's up to you, especially if you have a calculator. But the process that we must employ to solve for x, that is to answer this question via proportion equation, all right, is to cross multiply. So we're going to do that. And on this side, I'm going to multiply diagonally, and I'm going to write the abbreviation for x. And then on the opposite side, I'm going to write this. 250 times 120. You can go ahead and multiply those things and you get a pretty big number. Or you can actually get away with just sort of superficially multiplying, which is to put the dot in between and go, yeah, then multiply technically. What eventually is going to happen is that you're going to solve for x. So that means, again, you're employing algebra, you got to get the 4 away from it. In order to do that, remember, how do you move something over equals ultimately? You perform the opposite operation. So if we cross multiply, these two things would be multiplied. And to justify moving 4, I'm going to divide by 4 here and divide by 4 here. Right? These cancel. X would be left after we simplify all of this gobbledygook here. Again, you might be a little annoyed and go, hey, how come you didn't just do the work, right? I just know from experience that I could spare myself from having to even use a calculator if I employ tricks. But if you don't feel comfortable, by all means, do 250 times 120, get whatever the answer is, and then divide by 4. It would be fine. In its factored form, as you see it here, I can now simplify a little bit if I want. All right? I could do what I didn't accomplish before, which is that I can simplify this. All right? 1 over 30. That means that it's just 3 times 25, which is 75. And then 2 extra zeros is 7,500. That's the answer. All right? That's the same result you would get if you did 250 times 120, and you get 30,000, and then divide by 4. you get 7,500. Right. You don't always. One thing that you have to sort of condition yourself and your students, especially little kids. All right. Don't gravitate always to a calculator. All right. You need the mental exercise. That's really what, more than anything else, what is good about math? It's the mental exercise. It makes you more mentally acute. All right. Algebra is, the history of math and whatever else is interesting, fun facts. All right, but the actual experience of math is what's valuable. The mental stretch. All right, it makes you smarter. All right, so don't deny a kid that or yourself. All right. All right. All right, an hour and a half here. Let me go back to the discussion of percent equations because I want to show you some derivatives, right? And then we can do some of these problems here. All right. Let me minimize this for a moment, and I'm going to show you this. Here's that diagram for percent equations, right? These are the general idea, right? There are different derivatives of the part equation, which are practical, right? Like if you have a problem that is asking you about sales tax, right? Or a problem that is asking you about discounts, or something called markup, or commission. All right. Sales tax problems by themselves, discount problems by themselves, markup problems by themselves, and commission problems are all just specific versions of the part equation, which means that it really is just a percentage quoted to you times some number quoted to you. It's two things being multiplied, right? What you could do is basically just sort of write abbreviations. So if you're talking about sales tax, you could just abbreviate it as ST, right? And then use this as a sort of a skeleton. It's going to be a percent times whatever price, right? For discounts, D for discount, it's going to be a percent times a price, right? But this will be subtracted later, right? Whereas sales tax would be added later. Markup is the amount of money tacked onto the cost of something so that a store turns a profit. For example, the actual cost of a calculator may be, I'm just guessing, $10, all right? And from the manufacturer, that's maybe what they will charge for it, A store will then add a markup dollar value to the cost so that they're not just breaking even, that they're making money, right? Which is why you could buy this calculator in several different places at different prices, right? Why? Because some of them have a higher markup value and others don't, right? If you want to know how much, right, this markup value is tacked on to the cost of something, all right, again, it's just a glorified part equation. So markup would be a percent, a markup rate that they decide times the cost of something, cost to them, right? And again, this would be added. added later to cost. Then there's commission. And commission is what a person earns as a percent, as a chunk of whatever is sold. So if you were in real estate, for example, those folks a lot of times they work on commission. It's supposed to make things make a person more competitive, right? Or hardworking, supposedly, right? If a real estate agent, negotiates a $200,000 house sale, right, they're not themselves going to walk away with $200,000, but they'll get a commission, a chunk of that, right? Which is why they like to, have it as high as possible. Anyhow, it's a dollar value, right? So you might just abbreviate it. C is equal to a percent of commission rate. All right, rates are percentages. All right, markup rate, commission rate, discount rate, sales tax rate, right? They're a percent. All right, times whatever is sold. All right. All right, it's a part of what is sold. It's some percent of what is sold. Okay, so just bear that in mind. You're going to be using the more often than not the part equation. All right. Let's see. There's other things like I'm a little short on space, so what I'll do is I'll pull up my bootleg paint for a moment. Where is that? There it is. And just show you that. Other equations that somehow involve a percentage would be something like simple interest. Which is abbreviated by the capital I, and it's P times R times T. All right. P stands for principal, and that's a fancy way of saying the original amount of money involved. All right. R stands for rate, and that's a percentage. All right. Either as a decimal or a fraction. And T stands for time, but time has to be in years. So if they quote months to you, like 18 months, for example, you have to assume that 18 months is you can translate it into a fraction of a year, an improper fraction would be 18 out of 12. All right? Okay. And then there's another one that might be practical to know. Percent change. Right. The simplest incarnation of this would be a difference divided by an original amount times 100, and that makes it a percentage. It's a difference between the original and the new, right? Okay. Now let's finish up some of these word problems, okay? And I'll talk about magic squares and then we're done. Okay. A new car costs $20,000. If the sales tax rate is 5.5%, find the sales tax. They're asking just for the monetary value. So again, the derivative of the part equation that we'll use would be this one. ST is a percentage times the price. All right. So in place of the percent, we might write this. 5.5% in place of the price, we'll write 20,000. And as you can see, it's just pure arithmetic. The only thing is that you kind of have some crummy numbers here. All right. What I'm going to encourage you to do is write things in that sort of quasi-fraction-esque style. That is to say, as a ratio, something with a line, a top and a bottom. And in the case of a percentage, it's especially practical because if something is a percent, that means that its denominator is automatically 100. Right? So if you see any number up here, 5.5 in this case, it's just going to be 5.5 sitting on top of 100. You might go, well, yuck, that doesn't really make me happy. Why would you do that? Because when you're talking about like loans or car sales and stuff like that, a lot of times it's a nice round number, which means it has zeros in it. And again, to circumvent the necessity all the time of having to use a calculator or some tedium, even in doing a hand calculation, you could strategically rig something to make it easier on you. Right? If you're aware, firstly, and if you're comfortable. Right? Now, you could do brute force top times top, bottom times bottom, and simplify after the fact. Or, now that you've taken advantage of the fact that this is a percentage, so its denominator is 100, cross out 2 zeros here and here. And you're left with 5.5 times 200 instead, which is a lot easier to do, right? Some shortcuts, right? The tried and true thing would be to take 200 and multiply by 5.5, and then systematically do the work here, right? And there's no sin in that. Being able to do that is invaluable. But here's a shortcut, right? It's a non-zero times a non-zero. So just do 5.5 times 20, right? Or times 2, and then you could move some decimal places. All right? $10, $11, all right? All right. How many zeros were in here really? 2. So you have that figure to start with. How many decimal places do you have to account for? All right. Technically, there's 1 here, right? So it should be 1,100, I believe. Let's verify. All right. Now we'll do that as an afterthought. 5.5 times 20,000. Oh, pardon me, 5.5 times 200. I'm not even taking my own advice here. Think Donna. Yep, there you go. 5.5 times 200. All right, again, if you don't feel especially comfortable, do it the brute force way, all right? Top times top, bottom times bottom. You could simplify after the fact. That would end up being 200 or 110, 1,100,000, something like that, divided by 100. 5.5 times 20,000 is brute force. Let's see, 110,000, right? You'd end up with, in a case like this, 110,000, so top times top, and then 1 times 100 is 100, and again, you have that same thing, all right? Shortcut, pairs of zeros, it's the same figure. All right, 1,100 is what you would pay in sales tax. Okay. Let's see. Okay. In 1997, gasoline in New Jersey could be purchased for or at 87 cents per gallon. That's how cheap it was. That not really a nice gas station, with all due respect, but like a knockoff, like gas station that was like as dirt cheap as you can find it around here. All right. In 2013, it went up to 387. Now it's been kind of crummy. Express that change as a percent of increase or decrease. I'm referring to this. There's a formula you can borrow. Percent change is equal to a difference between the original amount and the new amount over the original amount times 100. If you get a positive, it's an increase. If you get a negative, it's a decrease. All right? But you have this, in theory, this skeleton to flesh out if you'd like. All right. So the original amount. Let's see. Is 87 cents, right? And the new amount is that. I'm gonna try to avoid. Let me do one thing different. I'll put new in front because if I don't, I'm gonna get a negative where I shouldn't. All right. New minus the original. All right. So that means 387 minus 0.87 over 8.7. And the reason that this is encapsulated like this in parentheses is that you must simplify this before you multiply by 100. You're creating basically a fraction or a ratio, to be more precise. And then you're just going to present it in the style of a percentage, which is y times 100. All right. If you subtract 387 minus 87, what do you get? You get an even 3 over 0.87. Right? And then you could either brute force divide this or use your calculator. I'm going to cheat for the sake of time here. 3 divided by 0.87 gives you this figure. 3.4485 it looks like, 82. So you end up with 3.8, 3.4 rather, sorry. 448 times 100 has the effect of moving your decimal point two spaces, right? Which makes it there, which means that this is about 3.45%, right? Since it ends up being a positive, right, because it naturally went up from something small to something large, right? This is an increase, you would say. Right? Express the change as a percent increase or decrease. This is a percent of price increasing. 345%, yuck, right? Okay. All right. Here's an example of for the simple interest formula. Okay. Floyd takes out a loan of $3,500. He then pays simple interest at 6% for 4 years and 3 months. How much does he pay in? How much interest does he pay? All right. Simple interest is this formula to borrow. Remember, this is an amount of money, a percent, and this is time in years. Okay. So, what would you have? Again, start out with writing things in fractions, believe it or not. I'm going to use 3,500 because that's the original principal amount of money. So I'm going to put this as 3,500 over 1 times the percentage quoted to us is 6%. So I'm going to write that as 6 over 100 because it's going to be to my advantage to cross out the zeros. And then 4 years and 3 months have to be translated into something that would be like an improper fraction. Okay. This would be 4 whole years and then some fraction here, all right? The fraction would be 3 out of 12, right? 3 months out of a total of 12. So that makes that 3 over 12, right? If you simplify it, that makes it 4 and 3, pardon me, 4¼ right? Because 3 divided by 3 is 1, and 12 divided by 3 would be 4. Now to convert that to an improper fraction, just for the practical reason here, you multiply these two, and you get 16. Added to that would give you 17 over 4. Okay, so what do you end up with? So I'm going to put that here. 17 over 4. Okay. And now I have a fraction times a fraction times a fraction, which again may not be anybody's favorite thing, but believe it or not, there's some little tricks here that can help a lot. All right, let's start with this. All right. Since I put the percentage in the style of a fraction, the zeros that are here would naturally cancel these zeros here. The minutia, the reason why, if you're curious that would work, is that again, it would be like cross-simplifying, all right? And that is really dividing without consciously thinking about it. It would be like dividing by 100 here and dividing by 100 here, okay? That leaves you with 1, 1, and 35 and 6, all right? You could get away with simplifying these two things just a little bit as well, all right? They're both even, which means they're both made of the number 2, which means that you could at least simplify by dividing this by 2 and leaves 2, and dividing this by 2 and it leaves 3. All right. So you can't get rid of it entirely, all right, but it helps a lot, all right? So what do you have then, all right? You have realistically 35 times 3 times 17, whatever that is on top, and then left over 2 times 1 times 1, which is just something cut in half, all right? If you feel more comfortable just doing it with decimals, 0.06 would be the decimal. And for this, it would be 4.25 for 4¼ right? Anyhow, I'm going to do it this way, 35 times 3 times 17, and you would get this. 1785 would be the figure on top, and then half of that would be dividing by 2. And I got a syntax error, there's a ding dong here. And you get this, 892.50. So $892.50, right, would be the interest that the person Floyd pays. Okay. All right. One more of these, and then we'll shift gears. All right. Back to this again. All right. Translating a little bit more. Plainly using suspect phrases, all right? And I'll use marker here to illustrate. The sum is a bunch of things added of 3 consecutive integers. Let's call these I, is 87. So all of this stuff, all right, would be 1/2 of the equation. And whatever is following it is just this stubby 87 here, right? This is a problem, since it's not too descriptive, where you could start out, right? Start out using 3 distinct letters, if you'd like, right? But ultimately, translate all into just one letter. That's a mouthful, so let me say that again. Right? You can start out using 3 distinct letters. All right. If you're talking about a sum of 3 consecutive integers, all right, it would be, let's just call it, x plus y plus z, if you like. All right. You can do that, right? A sum implies addition, and if it's 3 distinct things, it would be this distinct thing, this distinct thing, and this distinct thing. Never feel bad if you do that, right? Or if you're even more verbal than that, you spell out a whole word, first thing, second thing, third thing. What you must do ultimately, because you don't have something called a system of equations, is that you have to translate everything into just one letter. All right? If we're talking about consecutive things, what does consecutive mean? This means one immediately follows another. So there's no space in between them really, just the amount of one. So let's start with this. I for the first one, second, third. That's the first integer, right? The second one would be how far away from the first. The amount of one if they're consecutive. So the second thing you could call I plus 1. Right? The third thing is how far away from the first. Again, it's all referring back to that one thing. It would be 2 away from the original. So you might call this I plus 2. Right? And now you have this equation. Right? You have the original plus 1 is the second integer. You have the third, which is in reference to the first, I plus 2. All right? Now, because it's algebra, you have to combine like terms, which you may be a little rusty on, but let me remind you, all right? If you have like terms, which is essentially same letter, and technically the same degree, which you don't have to worry about in this case, you can add or subtract. So how many I's do you see here? There are 3 I's. Right? Add the other things. 1 and 2 would be 3. So you have this equation. 3I plus 3 equals 87. What this is going to solve for is just the first one. But you have expressions that equate to the second and an expression that equates to the third thing. So you can figure out all 3 things ultimately. Okay. So let's do that now. I need a little bit of space, so I'll do this here. 3I plus 3 is equal to 87. The way that I like to solve equations is to build sort of a table like this. So I always try to clearly define where the middle is, which is not really balanced here. But wherever the equal is, draw a little dashed line and leave a space here. All right? Move this 3 first. You justify moving this from here to here over equals by opposite operations, and you do so by balancing. Something minus itself cancels, then you perform the actual arithmetic here. 87 minus 3 would be 84. Right? This is left over, 3I, and then you have this equation. 3I equals 84. How do you move the 3 from here to here, over equals again? You perform the opposite operation, which in the case of a number pressed against the letter is the opposite of multiplying. So you would divide by 3 and divide by 3. They cancel, and you're left with what you're looking for, which is the first integer. All right. 84 divided by 3. 3 goes into 8 and roughly 2 times with a little 2 left over. 28. All right. If the first one is 28, and these are consecutive, that would be 28 plus 1, which would be 29. And the second one after that would be 28 plus 2. This would be these 3 integers, 28, 29, and 30. Okay? I'm going to, when I do my 090 video, which will probably be tomorrow, I'm going to review a lot of algebra. So if you feel a little sketchy, you're welcome to take a look at that. Now the very last thing is just because it might come up when you're doing your MyLab homework. There's this thing called magic squares, so I made a little chart here. All right. All right. What are magic squares? Imagine a single player, that is, you're playing by yourself, tic-tac-toe with numbers, right? And what you want to get in the row, column, or diagonal of three things is sum equal sum, meaning these things added together, three in a row, right? Or column or diagonal. Here is an example, all right? Suppose you're given the set of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, all right? And you are tasked with completing the magic squares diagram here, all right? Here's a little strategy, all right? Put them in numerical order. They happen to be in numerical order to begin with. All right, good. This is sort of a preliminary step. Figure out what is the middle quantity. That's the middle quantity in numerical order. And then write that middle number in the center square. So you're going to put the 5 here. All right. Now, using this middle number, determine several possible combinations of 3 numbers. All right. Meaning that you're going to use 5 every single time, but then 2 other numbers in tandem. All right. Now, to make it a little bit easier, what I would do is this. Try using pairs of numbers taken from the ends, right? Meaning a large thing and a small thing in tandem, right? To help you along, what I did was I made sort of this little sort of scaffold here. All right, I should shrink this just a wee bit. There you go. So we have established that a 5 goes here, all right, which means that if I'm doing some calculations to figure out how this is going to work, all right, 5 is going to be included every time. I put 5 of these little bullet points here for scratch work, but you only need 9 really. All right, so let's take the ends here. So if it's 1, 2, 3, 4, 5, 6, 7, 8, 9. The very largest thing, all right, would be, if you're forced to use 5, it would be 5 plus 9 and 8, right? Let's not do that. Let's instead use pairs of numbers from the ends. So let's try this. Everything is going to use 5 because it's in the center. Well, let's try this, 1 and 9, all right? If I do 1 plus 5 plus 9, what quantity am I going to get? Right? 1 plus 5 is 6, and 6 plus 9 is 15. Right? Now, before I start filling this in, and I would do this with a pencil, all right, let's see if we can keep getting 15s here. All right? Another possible combination would be something from the low end and something from the high end. Right? 2 plus 5 plus 8. 2 plus 5 is 7, and 7 plus 8 would indeed be 15, so far so good. Okay. Let's take another, something from the low end of the pool here, and something from the high end. All right. 3 plus 5 plus 7. All right. 3 and 5 is 8, and 8 and 7 is indeed 15. Cool. All right, and that leaves one other possibility. Let's see. 4 and 6, all right? So I would immediately have 4 plus 5 plus 6, which would be 9 plus 6, which is indeed 15 again. Very good. That seems to be the thing that is going to be the sum. The sum seems to be 15, all right? That is what is consistent. All right, so if this is going to be a true magic square, what that means is that it's going to be 15 diagonally this way, 15 diagonal sum this way, 15 column this way, 15 row this way, and each of the other rows and columns. All right, so let's see what we can do here. Alright. I'm gonna again stick with the middle here. Alright. Let me try the intuitively 1, 5, 9 column. And this would be 15 that way. And let's see. Something that I could get away with. Let's see, what else? 4, 5, and 6. 2, 5, and 8, right? 2, 5, and 8 here. I have to be careful because if I put, just say, for example, let's just say that I did what was in blue here. All right. And I'll put this in red. All right. Just to show you that I used it. If I were to take this one, 2, 5, and 8, and put it here, it would certainly be 15 that way. But it may not jibe with this. Right? Because if I ended up having an 8 here, right, it's not necessarily going to be helpful to me. Right? So let's see. 2. Let's take something from the small end here. Let's try this diagonal. All right. I put a 2, a 5, and an 8 here, then I got 15 going that way. Okay, so far so good. Let me try. If I did 3, 5, and 7, I may end up being in trouble. Let's see. 4, 5, and 6. Let me try that one. If I did this one, 4, 5, and 6, and I put it here like this, that's going to be 15 again, but it's not going to work with this row. What I might try is switching the position of these two. All right. And I'm getting in trouble though. That's going to be 9 and 8 is already going to be 17, so that's not going to work that way. So what I have to do is, before I jump the gun here, let me do this. I'm going to put this 8 here and this 2 here instead. Alright. That would be 15 that way. Alright. I'm trying to keep large numbers away from other large numbers. So 8, 5, and 2. All right. Let's see. Let's try. Four, 5, and 6. See if that works. 4, 5, and 6 would be 11 plus 4 is indeed 15. That works. But now I have to verify. 8 plus 1 is 9. 9 plus 6 is also 15. Very good. And 4 plus 9 is 13 plus 2 is also 15. So far so good. You have to tinker with it. All right. All right. Now, what can I work with here to fill in these two and satisfy that? The diagonals are okay and the middle is fine. Let's see. If I use 3 here, that's the one thing about the magic quiz I left out here, that you have to use every number once. Alright. So 8 and 3 is 11 plus 4 is 15, that works. And what's the one thing that hasn't been used yet? 7, right? So if I put 7 here, is that going to be okay? Let's see. 3 and 5 is 8, 8 and 7 is 15, that's correct. And let's see, I gotta confirm this one. 6 and 7 is 13, 13 plus 2 is 15, looks like it's okay. There's probably more than one arrangement of this, alright, but that's one that happens to work. Okay? Sorry, I kind of muddled through that. Alright, let me just reinforce this, right? You want to use every number once, right, in the set, right? You want to put the middle quantity, whatever it is numerically, in the center, right? And then I would sort of try to do, I went this way, and then diagonally like this. That seems to work for me. Alright, so across the center and then diagonally. Alright. And that's that. Alright, let me adjust the lights here. And I'll turn up this projector now. 2 hours, so good. The board is so dirty. Alright, for homework, alright, remember if you haven't yet, alright, you want to establish a MyLab account by Sunday night. Assuming you have done that already and you want to keep current with the schedule, alright, work on section 1-3 and both parts of 6-3. Okay. What I'm going to do myself is for the 090 supplement, there'll be a video for algebra review tomorrow. If you want to check that out, go ahead. Alright, it's open to anybody who'd like to see it. Right, it's on the internet. But for you folks in 090, if you find that useful, that's why I'm doing it. Alright, so we'll just review some techniques and stuff like that. Okay? Alright, thank you guys for sticking with me. Alright, and I'll see you again tomorrow and then Tuesday next week. Okay? Tomorrow, if not Tuesday next week, for all of you. Alright? Be careful out there.